This video is part of our series on making 5-point stars, and in particular, in this video, I'll demonstrate how to accurately cut these segments. Now, the technique that I've developed is based on a template, which is basically a 36, 54, 90-degree triangle. And with this, I can set up the fence on the table saw sled at 54 degrees and make the first cut. And at 54 degrees aligns the arms of the star so that I get a line across here. And that's the first thing I'm looking for. The next thing I need is an accurate cut at 36 degrees so that all of these segments come together to form a nice tight turning blank. There's no gaps. Okay? And if I can make these two cuts, then I can form a nice looking star. Okay? So this video will start by me crudely setting up these angles of 36, 54, and 90 on the table saw sled. Then I'll go back and refine the 36 degree cut. After that, I'll refine the 54, and then finally, I'll refine the 90 degree cut. And I don't need the 90 degree cut to make the star, but it's such a useful angle to have, I might as well show you how I do that. Okay. It turns out if you can come up with this template and you don't have to build it yourself, then you don't need to watch the rest of this video. If you have access to a CNC machine or a 3D printer, you can quite easily make one of these templates. If you have access to a milling machine, you can use this technique to make one of these. Take a piece of 1/2 inch aluminum or 3/4 inch MDF and bolt that to the table on your milling machine. Sneak up on a point and set your dials to 0, 0, and then come over 6 inches, drill a hole, and pound a pin in there. 6 times the tangent of 36 degrees is 4.359 inches. So you come back to 0, bring this up this distance, drill a hole and pound a pin in there. And with those 2 pins in place, you can take your stock, bring it up and clamp it. When you make the cut along the x-axis, you'll form this 36 degree angle. When you make the cut along the y-axis, you'll form the 90 and the 54 degree angle, and that will give you this template. And you can make once you have these pins set, you can make as many templates as you want. Okay. If you don't have access to one of these, either a CNC, a 3D printer, or a milling machine, I'll show you in this video how I make these. If you do have access and you can make your own template, it may be worthwhile to watch the section on refining the 36 degree angle. That way, if for some reason you do form a star and it has a large gap, you'll know how to refine that angle, recut everything, and close that gap off so that you can always have a good looking star. Well, with that, let's get started. This is my table saw sled with the fence removed. And the first order of business is defining where I'm going to put this post, and then drawing through that point a line, a 0 degree line that's parallel to the kerf. And then from this line, I'll define 36, 54, and 90 degrees. Okay? And this is the first pass at setting these accurately. This is a mock-up of the table saw base that I just had on here. So here's my runner. I need to define this to be 0 degrees, so I'll raise the blade, pass the base through there, and cut this off. And then I can bring my table saw fence up, lock this in place. Now I know this is at 0 degrees, so if I use a framing square and take the 1.5 inch thick arm, use that to draw a line along here. Then come up about 4 inches from the edge of the base. Draw a line at 90 degrees. That will define where I want to put that post, and it will also define a 90-degree line. This line that I drew parallel is 0 degrees. Now if I used a tangent function, I can measure up 15 centimeters, and I use centimeters instead of inches so that I don't have to fool around with the fractions. I have a scale that's graduated in centimeters that I can use. So I'll come up 15 centimeters, and I take 15 centimeters times the tangent of 36, and that's 10.90 centimeters. I'll measure that distance here, draw this line, and that's 36 degrees. Then 15 centimeters times the tangent of 54 is 20.65 centimeters. I'll measure that distance and draw this line, and that's 54 degrees. And that's all I have to do to get a crude estimate of 36, 54, and 90 degrees. Just use the tangent function. Now it's time to refine that 36-degree angle. So I've set the pointer on my fence to 36 degrees. I'll lock that in place with the table saw fence. In order to refine that angle, I'm going to cut 10 wedges, put them together in a circle, and then I'm going to measure the size of that gap. I'll do a short calculation, and that tells me how far to move this fence to close this gap off. I want you to note this is not a trial and error thing. I'm going to make one set of cuts, and if I do it precisely enough, I will know exactly how far to move this fence to close this gap off. So it's not trial and error. I measure, I move, and I know I'm going to be right. Okay. So I've cut 10 pieces of plywood. And basically, I just cut a long strip of plywood off of some scrap and cut off 5 pieces, rip those across the diagonal. I have no idea what this angle is. It's close to 36, but it's not real close to 36. So these are going to be my test pieces. But the idea, I'm going to cut all of these on this setting, and then I'll determine how to correct that. But as I push this through the blade is going to push this piece downward. And the only way for me to stop that is to push down with pretty good force. And I don't want to do that. So I'll come up with this clamp, and I understand this is overkill, but it does the job. I've got a carriage bolt with a pine 2x4 cylinder that I've cut up. That's captured by a nut. I have a piece of hard maple, and I've drilled an oversized hole, filled that with epoxy, and then drilled and tapped that to accommodate this bolt. On the other side, I cut a cross, and into that cross I put a pine cross that I've embedded a rare earth magnet in, and that magnet just ensures that this piece of pine stays up inside that and stuck to the bolt. Okay. This is overkill, but it works. The next one I make will be just one slot. I don't need to cross. Okay. And the idea is that when I turn this bolt, this goes straight down. Okay. And it also, I know that this is the lowest piece of metal on this jig, so I can cut anywhere on this jig except for the top of this plunger. Okay. Now let me set that where I want it. This is not the most elegant way to do this, but it works. Okay. Right there. Now, in order to help me align these in a circle, I want to cut each one of these identically, so I'm going to use a stop block. And the stop block, I've chamfered these corners, so if I get dust or chips in there, it won't hold this off and change my position. So set that up. Okay. So now I'm set up and I'm ready to start cutting it. I understand that you may think this is overkill, but I've learned that the more precisely that I cut these, the more likely I am to be able to correct that error in that angle with one step. And I get better stars out of that. So this may be overkill at this stage, but this is the way I do it, and it's been working well for me. Precision is important. I have to make sure that this face of the fence is clean, that the corner down in there is clean and free of dust. In fact, that this is clean and free of dust. So let me set my table saw hat. And we'll be ready to start cutting. Now let's put these in a circle and see how we did. First thing I want to do is check the precision and see how well I cut these all the same. So, the same along the bottom. They're all the same along here. They feel the same along there. So all of these have been cut to the same angle. I could take 5 of these, put them against the straight edge, because 5 of them should be 180 degrees. And you can see the gap, so I know that I'm off. I prefer to do all 10 because it's going to double the size of that gap, and I'll get a more precise measurement. Okay, I can see that I have a gap, and in order to measure that gap accurately, I need to tape all of these together. So I'm going to line the back side of each one of these, pull it tight, and tape it together. Now I slide the last piece in place. that. I want to tape these so that each one is pulled together tightly, and that forces all the air into this gap. And this tells me everything I need to know to adjust that table saw sled. So the first thing I want to do is measure the gap. I read 0.104 inches. Measure that again. 0.104 inches. And that's over a gap this large. It's not long enough. From here to here is 7 5/16. So this is the data that I need to tell me how to correct that angle, and that'll be the next section of this video. Well, here's the gap that we measured to be about 0.104 inches, and that occurs over about 7 5/16 of an inch. So given this information, how do I correct that angle? Now, this page shows me everything I need to do. Here's an example where I have 10 segments, and instead of having a 35-degree angle, instead of having a 36-degree angle and forming a perfect circle, they have a 1-degree error, so this is 35 degrees, and the cumulative error give rise to a gap that's almost 0.7 inches tall out here. So if I take this wedge and draw it over here, D represents the distance over which this gap occurs, and I'm going to call this height 10E, or 10 times the error associated with one segment, because each of these 10 segments contributes equally to this error. Now, I want to discover how do I correct the table saw sled for one segment. So I take this number, 10E, divide it by 10 because I have 10 segments, and I draw a little wedge down here. Then I project that wedge out. And these two triangles are similar. The triangle here is similar to the big triangle here. And that lets me say that the small error divided by the small distance is going to equal to the large error divided by the large distance. This is important to me because down here I'm thinking this is my fence. So here's that bolt that's the pivot point, and this distance D is 10 inches, which is the length of my fence. It's where I have that line drawn around the fence. And E is the distance I need to move that fence to correct for this original error. And I can calculate capital E in this manner. It's just a ratio of two distances multiplied by this distance. Okay, so this is the important equation. And if this is an 8-inch diameter circle with 1 degree error per segment, I'm going to have about 0.7 inch gap here. If I take those numbers, run them through this equation, it tells me at 10 inches I would have to move the fence 17 or 0.17 inches. Okay. Now this is a huge error. Okay. Let's take a look at our specific case. Our error occurred over 7 5/16 of an inch, which is about 7.3 inches. My fence is 10 inches long. The gap is 0.104 inches. If I divide that by 10 to find the error associated with each segment, I come up with about 10 thousandths of an inch per segment. If I run through this calculation, I discover that I need to move the fence 14 thousandths of an inch. That is 10 inches from the pivot point. I want to move that fence 14 thousandths of an inch. And that's certainly a doable thing. I'm going to have a hard time measuring something that small precisely and accurately. So I may have to try 2 or 3 times, but I can eventually get it close enough that I'll be happy. But what if I could mimic a fence that was 320 inches long, something that's incredibly long? Well, if I run through the math, I'd discover that I'd have to move that fence 0.445 inches. And there's actually a way to do this. If I set up a laser pointer on this pivot point, shine the laser onto a mirror that's 160 inches away, return that laser beam to here, that's a 320 inch round trip. If I move the fence out here 14 thousandths of an inch, it will move this dot, that laser dot, 0.455 inches. This I can measure easily. This I have to use calipers and be really careful. And I'll show you how I do both of those. For quick and dirty work, I just move the fence. For really accurate work, I set up the laser and follow that laser dot. And I'll show you how to do both of those. We know we need to move this fence 14 thousandths of an inch, 10 inches from the pivot point. So here's our pivot point, and the arm on this fence is 10 inches long. And that's what this line wrapped around here represents, the 10-inch point. Okay? But I need to figure out which direction to go. Now, if you recall, when we put those wedges, those segments in a circle, the gap was in the center, which means there was too much material on the outer edge. That means I don't need to remove material here, but I do need to remove it out here to close that gap, which means this fence needs to move toward the blade. It needs to swing in this direction. Now the question is, how do we go about doing that? And I need to move 14 thousandths of an inch. The best way that I know to do that is to put a dial indicator out here. Get that set to 0. Then I can loosen my clamp and move this fence back and forth until that dial indicator reads 14 thousandths of an inch. And I can clamp it. And if for some reason the fence moved when I clamped it, I would know. The dial indicator would tell me. And I could just continue fooling with it until I get it clamped at 14 thousandths of an inch from where it originally started. And then I know that I've corrected for this error. Okay? I don't have a dial indicator, so I've got to come up with something else. Quite often, people put a stop block up here, and then they go looking for things that are 14 thousandths of an inch thick. And it turns out 5 sheets of this notebook paper are 14 thousandths of an inch thick. So I could clamp this in place, butt it up against the fence, clamp it in place, unclamp the fence, move it forward, put 5 sheets of paper in there, pull it back and clamp it. And that would give me about 14 thousandths of an inch. That's fairly inaccurate, however, and there's no way for me to be sure that I've actually clamped it where I want it to be. Another option is to use my calipers, and I have to pull this back so I can get the calipers in there and make a reading. And I would clamp this, make a reading, add 14 thousandths of an inch to that number, and move the fence and go on with that. Turns out, with the tools that I have, this is kind of a tricky measurement to make. I can do it, but it takes a while to get it accurate. I can get close quick, but to get it really accurate takes a lot of effort for me. There's another way to do this though. What if D is 320 inches long? Well, let's explore that option. Made a block of wood where I drilled holes so I can sit over the post and the nut and the washer. This is a laser pointer. I'll turn it on, hold it on with this piece of tape. And now I have a mirror on the other side of the room. And here's the screen. Let me push that forward a little bit. And there's the laser point. Now, looks like it's drifting just a little bit on me. It may take a minute for this laser to quit drifting, so I have measured from the front of the table saw to that mirror is 153 inches, so the round trip is 306 inches. I measure from the front of the table saw to the laser is 10 inches. I have 306 plus 10 inches. And now I need to measure from the front of the table saw to this screen, and that's 15.5 inches. Add these up. That's 331.5 inches. So I need to calculate .0104 divided by 7.3125 times 331.5 equals. That gives me 0.471 inches. That's how far I want to move that laser dot. And when I rotate the fence this way, the dot is going to move this way. So there's my laser dot. Now, 0.471. 0.47. I can't see well enough to do the 1. Set this here, and I need to take a peek in the camera and see if you can see that dot. No, you can't. Oh, I'm in the way. I'll dim the lights until you can see that dot. Okay. Now, I found the laser dot and put a line there. Then I moved over 0.471 inches and put another line. Now I'm going to loosen the clamp, rotate the sled until that laser dot is on this other line, and then lock it back in place. Okay, there it is. So I have moved that and hopefully corrected that error that we had before. You'll also notice I can take this sled and rock it back and forth, and it does move a little bit. It moves back, it rocks up and down, but the motion back and forth, side to side, that's indicating an angular error, and it's actually quite small. So I'm happy with how stable this sled is. Okay, the next thing to do is cut those 10 pieces again and see how well we did. Okay, I have the angle corrected. I've got my stop block in place, and I have my clamp set up just like I did the first time I cut these segments. So let's fire this thing up and cut them again. see how we did. Hey, here's the moment of truth. I think that's about as good as I'm ever going to get it. The ultimate test is when I pick this up and hold it up to the light and look through it. So let's see if I can flip it over and tape it a little bit more and get it stable. Ooh. That didn't go so well. Let's... Try that again. Okay. Got it taped on both sides, so maybe I can pick it up and look through it. I can see a little bit of light coming through in some places, so it tends to be centered in the middle, so I didn't cut quite enough off. It's hard to tell how far off I am with something this big because as I hold it up, it flexes and moves. I'm going to call this good enough. Okay. So now I'm pretty confident that that angle is set at 36 degrees. Well enough that I can make a star. So if you imagine a star this big around and I look at how closely matched these are, I'm pretty happy with that. Fact is, even if I made a star that's 16-inch diameter, this would be good enough. So for 99% of what I do, this is plenty good. Given that, I'm going to go ahead and cut the 36-degree angle on two of these plastic triangles that I want to make. Let me get that done. Now that I know that this sled is accurately set to 36 degrees, I'll go ahead and cut the 36 angle on these plastic triangles. Now I'm ready to set my fence to 54 degrees and refine that angle. And I'm going to do that using these 5 triangles. This is the blade. I set my fence at 54 degrees and make a cut. This angle is 54. Flip that triangle over and make another cut. This angle becomes 54 degrees. Now, if both of these angles are 54 degrees, I know all 3 angles have to add to 180. That forces this to be 72 degrees. And it turns out that 5 times 72 is 360. So these 5 triangles will join together to form a perfect circle. So the game plan will be to cut these angles and adjust the fence until these angles form a perfect circle. And then I know this is 72, and I know that these are accurately set to 54 degrees. So that's how we're going to adjust that fence to 54 degrees. Okay, I have my table saw sled fence set at 54 degrees. I have my triangle marked so that this mark always goes against the fence. Side 1 guarantees that I cut this side. Side 2 guarantees that I cut this side. And that way I don't cut one side twice and leave this one in error. Okay. I have stop block set up. I have my clamp ready. So let's go ahead and cut these. it turned out. Okay, we have a gap. Again, I want to tape everything together, force the gap into one, force all the air into one gap. So there's the gap. And this is what we need to correct for. Okay. Call that 74 thousandths of an inch. Do that again. This flexes a little bit, so I need to be real careful. Gently measure that. It says 73. I'll leave it at 74. 73, 74. I'm not that worried about it. Now, how long is this distance? .644. Okay. It turns out I can correct this gap exactly like I did the previous one because there are 10 cuts required to adjust this angle, so there's 10 times the error associated with that gap. So just like in the previous case, when I was adjusting the 36-degree angle, I need to divide this error by 10. Okay. So let's do that math. Over a length of 4.6 inches, I have an error of 0.0074 inches, or about 7/1000 of an inch. Now if I come out to 10 inches, that error is going to be little e over little d times big D, which is 0.0074 divided by 4.644 times 10 inches. And that's going to equal okay. This calculation is exactly like the previous one when we were correcting the 36-degree angle. I have a gap of 74/1000 of an inch. I'm going to divide that by 10, and that's the error per cut. Okay, because I made a mistake when I measured the gap previously. It turns out the first time I measured that gap with the calipers, I spread that gap apart. I thought I had closed it back up, but I didn't. Oh, I took everything apart and taped it on the top and the bottom to give me a little more rigidity. And when I measure that gap now, I get 61/1000 of an inch instead of the 74. So if I run this 61/1000 through the calculations, it tells me I now need to move the fence 13/1000 of an inch, 10 inches away from the pivot point. It turns out if I take 5 sheets of paper and stack them on top of each other, that's 14/1000 of an inch, which I'm going to call that close enough to 13. So I'm going to use these to help me move the fence 13/1000 of an inch. I'm also going to set up the laser like I did when we when we corrected the 36-degree angle. And if the distance is 331.5, just like it was previously, that laser beam needs to move 0.435 inches, which is within a couple of thousandths of 7/16 of an inch. So I'm going to set up to do both of these, and I'll move the fence according to these sheets of paper, hopefully about 13/1000 of an inch, and I'll monitor how far the laser beam deflects during this and just see how close it is to 0.435. That'll give me a check of this procedure where I used a paper to move the fence. So that's the first problem I need to clean up. The second problem is we have to decide which way to move the fence, and it may seem obvious, but we need to think about that for a minute. I have a gap on the outside, and that means as I come around, each of these segments is less than 72 degrees. If it was exactly 72 degrees, of course, this would close up perfectly. Because there's a gap, I know that this angle on each of these segments is less than 72. Now, if this is less than 72, it means that the 54-degree angles have to be greater than 54 degrees. So these are greater than 54. So I need to decrease the angle where I'm cutting. So I rotate the fence toward the blade. Let me do that one more time. As I come around, I leave a gap, and that tells me that this angle is less than 72 degrees. This angle being less than 72 means that this is greater than 54 degrees. Okay. So these angles that I've cut are greater than 54 degrees, so I need to decrease that angle by rotating the fence toward the blade. I'm set up now to refine the 54-degree angle on this fence. I had the laser set up, bouncing off a mirror and coming back to this screen, and the total distance is 331.5 inches. And the distance between these two lines is 7/16 of an inch. And that's the distance I want that beam, that laser spot, to move when I've adjusted this fence. Now, I'm also going to try to move the fence by using 5 sheets of paper. So I'm going to take this piece of wood that has a rounded edge on it, butt that up against my fence close to the 10-inch mark. I want to make sure that's tight up against there. Now I can loosen this clamp, slide the fence forward, insert those 5 sheets of paper and pull it back. And then I want to pull this fence tight against the paper. And tighten this clamp. When I do that, it looks like my laser is almost far enough over. So I may have pulled back a little bit too tight. So I'm going to loosen this clamp. Set the laser where I want it. And tighten it down. I'm still pretty tight on that paper. Inserting the paper or any other spacer in here works fairly well, but I always end up with some uncertainty into exactly how tight do I pull this. And I don't want to pull it too tight and crush wood or crush the paper, but I don't want to leave it too loose and leave some slack in there. And I never quite know exactly how to go about I don't know exactly how much pressure to apply. The reason I like the laser so much is that it's not about pressure or how much force I apply. I just look at the dot, tighten my clamp, and if that dot is where I want it, then I'm good. If not, then I know to move it. And it takes my judgment out of the equation. I don't have to judge forces on here. Okay. If I had a dial indicator, I wouldn't have to do either one of these. I'd simply put a dial indicator on here, move it 13 thousandths of an inch like I'm supposed to, and I would be done. So that may be one of the next things I purchase, is a good dial indicator. Okay, that takes care of it, the refinement on this. Let's cut those segments and see how we did. Here are the 5 segments taped together, and I went ahead and taped them on both sides. And when I just look at it from here, I have nothing to complain about. And if I hold it up to the light, I can just see real faint light here and just a little bit here. So either I have a crooked cut or I need to modify that angle by less than 1/100th of a degree, and I'm not going to worry about that. By the time I put glue in that joint and squeeze it together, you're not going to see it. And it could, in fact, just be something off on the cut, or even conceivably some dust in there. So I'm going to call this good enough. So now that I know that that 54-degree angle is set as accurately as I'm ever going to get it with my tools, I'm going to go ahead and cut those triangles. So I have my triangle set up, and I'm going to cut this 54-degree angle. And if everything is done right, it'll turn that into an accurate 90-degree angle as well. Okay, so let's go ahead and make these cuts. So this now should be an accurate 54-degree cut. This should be 36 pretty accurately. Now I'm set up so we can refine the 90-degree setting on this fence. And the technique's pretty straightforward. I start with the board and I want to make a good clean straight cut across here, and then I'll mark this side on both sides, and this stays against the fence. I'll start by making a cut, then I'll flip the board over, keeping my mark against the fence, and make another cut. Now if this fence is at 90 degrees to the blade, both of these cuts will be straight, and when I measure the distance here and the distance here, I get the same number. These two sides are parallel. Then I know that I have a 90-degree fence. More than likely, I'm going to start off with either the side splayed in or the side splayed out. And by making the measurements here and here and subtracting the two, dividing that by 2, that will tell me how to move this fence. So let's give it a try. I've measured this distance and found out that's 5.015 inches. Okay. Now let's measure here. .600. 5.600. At the top, 5.600. And by the fence, I get 5.610. 5.610. So I have a situation where I'm narrow at the top and wide on the sides. When I subtract these two, I have 10,000ths of an inch difference. And this 10,000ths of an inch comes about because of 2 cuts. So if I take that and divide it in half and come up with 5,000ths of an inch, I can go back to my old equation where the error that I need to move the fence is this little e, and that's equal to e. Divided by little d times the 10 inches for the length of my fence. That's 0.000 0.010, 10,000ths of an inch. So I need to move that fence 10,000ths of an inch. And let's see if I can find something in the shop that's 10,000ths of an inch thick. Oh, before I get carried away, I need to figure out which way to remove the sled. The top is narrower than the bottom, and that means this sled is already tipped in this direction. The sled is tipped toward the blade, and I need to move it backwards. So I need to find something that's about 10,000ths of an inch thick. And there's 11,000ths, so 4 sheets of paper. That's 11,000ths. Okay. So again, I have a piece of wood that's rounded. I'm going to put this up there, clamp it. Make sure I'm tied against the fence and clamp it. Take my 4 sheets of paper. Slide that up snug. That's snug. Let's cut it again. This distance is still 5.015 inches. Let's see what these other dimensions are. Five point 301. 5.301. And on the bottom, and 5.302. So the top and the bottom are the same width to within 1,000th of a degree. I seriously doubt my ability to accurately measure that in wood because dust and chips and fuzz and my inability to control the calipers that accurately over that distance. So I'm going to call that good enough. And now this fence is at 90 degrees to the blade. And I can set up to trim those triangles now. Can't see any problem with that, so I'm going to say that's a good cut. So, I hope you noticed that all three of the calculations were exactly the same. I would measure a distance over which the error occurred. Then I would determine the error itself and then divide by how many cuts were involved in that error. In this case, 2 cuts. This first cut caused this amount of error. The second cut caused this amount of error. And that gave rise to 10 thousandths of an inch difference here. So I divide that by the number of cuts, and that's the little e, the error that goes in this equation. And that is the only thing that's different between the 3 techniques. 2 of them I divided by 10, and this one with only 2 cuts I divide by 2. But the concept is exactly the same, and the mathematics is exactly the same. And this is a way that I can take these angles and correct them in one step. Instead of trial and error where I go back and forth, if I make high precision cuts and high precision measurements, I can quite often step from where I start to a final solution that's accurate in one step. And that way I take a lot of the stress and a lot of the work out of this technique. Now, I do need to acknowledge some folks. There's another way to set that fence at 90 degrees. Let me get my notes here. If you Google 5 cuts to a perfect crosscut sled, you'll be led to a video by William Ng, and he has a really good video on how to go about using 5 cuts to get even more accurate than this. And the math looks really difficult, but it is exactly what we're doing here, except you divide by 4. I mean, it's literally no different. Okay, the laser technique that I use, I didn't come up with that myself. That's by Steve Garrison from spiralsbysteve.com. If you search precision miter angles using a laser, you'll come up with his video, and that's where I got the idea. Oh. that's pretty much all I need to say about setting the angles on this fence and making these triangles. The only other thing you need to do is check to see how accurate they are. Okay, but if these are accurate, and they should be, if I did a good job cutting them, then I can make stars with these templates without a whole lot of fuss. And if I have to correct any of the angles at all, it's only the 36-degree angle, and I have to make one correction, and then I can cut the star. So I hope this demonstration has been useful, and hope it inspires you to go out and make a few stars and see if you enjoy doing it. We've seen each step in the technique that I've developed for making these stars, so now would be a good time to assess the overall technique and each step along the way. To assess the overall technique, we just examine the quality of the star. All the points come together in the center. There's a problem with chipping, and I expected that, and I can eliminate that by trimming these segments or just turning this and taking enough material out of the center to cut through those chips. When I look at the precision of the obtuse angles out here, I'm very happy with that. The points come together very precisely, and I'm happy with that. When I squeeze this blank together and look at it through the light, there's very little light comes through, and that tells me this is going to glue up and form a very good, strong turning blank. So overall, I'm very pleased with how this came out. So the overall technique is working well. As far as the design steps, it's quite easy to go from the dimensions of this star and the dimensions of the border to the dimensions of this laminated board. There's 4 equations that take me from this idea to this idea. And that's the simplest that I've come across. This board is easy to build, and it's easy to cut up. I just cut it up in 54-degree segments, and I do the cutting under the guidance of a template. So I use the template to set my fence at 54 degrees, and if you recall, the 54-degree cut doesn't have to be that accurate, so I never have to adjust this fence. If this triangle is well made, I set the fence, I start cutting, I'm done. Then I can set the fence at 36 degrees, again using the template. And here I need a precise and accurate cut. And if this template is made well, often I won't have to adjust this fence. It'll be close enough that I can make a good looking star just on the template alone. But if I do have to adjust the fence, I know a technique where I take those 10 segments, cut at 36 degrees, force them together, take all the error and force it into one gap. I measure the gap. I measure the distance over which the gap occurs. That allows me to calculate how much correction or how far I need to move this fence to correct for that gap. It's not a hit and miss guess kind of situation. You measure, you calculate, and you move this fence a known direction and a known distance, and that solves that error. And that's how we get these good, tight-fitting turning blanks. And that part of the technique is fairly well worked out and easy to do. A couple of times during the video, I've talked about a dial indicator and how it would save me some effort. Well, I broke down and bought one, and I set the dial indicator up at the 10-inch mark, and I calculated how far should the laser move if I moved this fence 10, 20, and 50 thousandths of an inch. And that would let me assess how well that dial indicator was working. And it turns out it worked really well. So this will probably become my go-to solution for adjusting these fences. It's quick and it's easy, and it has pretty good reliability, I think. So this will be my go-to technique. I now assess the sled itself. I built this sled to be quick, cheap, and easy. And under those conditions, I guess I'm pretty happy with it. This sled is solid. When I clamp this swinging arm and outrigger and bolt it down, this is rock solid. And this gives me the precise cuts that I need. Okay. It removes my skill from the equation. I don't have to run this through carefully. It guides me, and there's no slop at all in this. So that I really enjoy about it. It can also be accurately set. There's one problem though. This is MDO, which is basically plywood. And normally I will set this bench, dial it in to 36 degrees very accurately. And while it's still clamped, I'll take it to the drill press and drill a hole through the swinging arm into the base itself. And then I can drop a pin in there and know that this is accurately set at 36 degrees. We had a rain while I was filming some of this, and this sled moved so much that I couldn't trust that hole anymore. But typically what I do, if I'm using MDF, I'll drill this hole, I'll do the same thing at 54 degrees, and then when I'm ready to make a star, I don't need the template, I don't need anything else. I just come in, drive that pin in here, set me to the 54 degree angle, make my cuts. I can come over to 36 degrees and make my cuts, and I'm pretty sure that that's going to have the accuracy I need to make a good looking star without adjusting. If this was MDF, I could probably get away with it, but the plywood moved so much I don't trust it anymore. So the design I like, the principles on how it works I like. The material is the only thing I don't like about this sled. Overall, this is the simplest technique that I've come across to make stars. And I hope this has inspired you to make a few stars and just see if you enjoy doing it. And I hope I've also shown you each step in the technique required to make those stars to a high precision and high accuracy so that they look really good. And with that, I really appreciate you watching.